Exactly 100% of massive stars are mathematically destined to vanish into an infinite. Researchers at Birkbeck College proved that this total gravitational collapse is an unavoidable geometric consequence of general relativity. However, the proof for this terrifying cosmic trap was found while crossing. Roger Penrose was walking beside Ivor Robinson when the hidden topology of this single moment of clarity eventually earned him the Nobel Prize for proving that black holes are inevitable. Now, you have to understand the vibe of London in the mid-60s. In the physics departments of the era, there was a palpable sense of crisis brewing. For 50 years, Albert Einstein's General Relativity had been sitting on the shelf like it predicted things that nobody, not even Einstein, wanted to believe were physically real. Specifically, it predicted singularities. These are points where gravity becomes so intense that the curvature of space becomes infinite, and time effectively stops. Most physicists dismiss these as mathematical glitches. They reasoned that because real-world stars are messy, rotating, and asymmetrical, they would never actually collapse into a single point. They figured nature would always find a messy way out, a way to bounce back before the density became infinite. But as Penrose and Robinson reached the median strip of Tottenham Court Road, the chatter of the city faded into a background hum for Roger. He wasn't thinking about chalkboards or tensors, he was thinking about topology. He was a geometer who saw the universe through the lens of shapes and light paths. In that fleeting moment of silence between sentences, a specific mental image. This was a closed two-dimensional region, where gravity is so strong that even the light rays trying to flash outward are actually dragged inward. When they reached the other side of the pavement, the conversation resumed. Robinson kept talking, totally unaware that his companion had just rewritten the rules of reality in the time it takes to walk 10 paces. Penrose actually pushed the thought away for a few hours. He felt a strange, lingering sense of elation, but he couldn't quite pin down the source of his good mood until he was back in the quiet of his office later that day. He began to look for that flash again, retracing his mental steps through the London traffic. When he found it, he realized he had finally bridged the gap between 1915 and the modern world. He had found the mathematical proof that once a star collapses past a certain point, no amount of rotation or asymmetry can save it. The collapse becomes a one-way street to infinity. He had just proven that black holes were not just a quirk of the math, but a robust prediction of the universe itself. For 50 years, the most terrifying prediction of general relativity was treated like a family secret that you have to understand. When Einstein sat down in 1915 and scribbled out those field equations, he had created a masterpiece. It was a geometric description of gravity that was elegant, symmetrical, and deeply satisfying. But tucked away inside those equations was a ghost. It showed up almost immediately in 1916 when a German physicist named Karl Schwarzschild sent Einstein a letter from the Russian front during World War I. Schwarzschild had found the first exact solution to if you squeezed enough mass into a small enough space, the math simply broke. It gave you a point where the curvature of space-time became infinite. Density became infinite. Time effectively stopped. In this bizarre region, which we now call the Schwarzschild radius, gravity became so intense that not even light could escape. Einstein looked at this, and frankly, he hated it. He called it a Schwarzschild singularity, but in his mind, it was just a mathematical artifact. Think about the maps we use to navigate the Earth. If you look at a standard Mercator projection, the North Pole looks like a long, flat line across the top of the map. But a traveler who actually makes it to the pole doesn't fall off a cliff. It's just a coordinate singularity, a failure of the map, not the territory. For decades, the consensus in physics was that these singularities were exactly that, a failure of our mathematical map to describe a reality that would surely find a way to avoid such a mess. Nature doesn't like infinities. They are the universe's way of screaming that your theory is incomplete or that you've pushed the math in. In 1939, J. Robert Oppenheimer, the man who would lead the Manhattan Project, and his student Hartland Snyder tried to take the idea seriously. They published a landmark paper titled On Continued Gravitational Contraction, which used Einstein's own math to show that a sufficiently massive star, once its nuclear fuel ran out, would have no choice but to collapse under its own weight until it reached that infinite point. It was a dark, brilliant piece of work, but even then, the community found a loophole. Oppenheimer's model assumed a perfect star. It was perfectly spherical, perfectly stationary, and perfectly uniform in density. It was a physicist's spherical cow. Einstein himself published a paper in the Annals of Mathematics that same year arguing that such objects wouldn't form in nature because real matter has pressure and rotation. He believed that as a real star collapsed, the particles wouldn't hit the center. They would just swirl around it, like water missing the drain. This was the bounce theory, and it was championed most aggressively by the Soviet School of Physics in Moscow, led by titans like Evgeny Lifshitz and Isaac Kalatnikov. They argued that in the messy, chaotic reality of a real star, things would never be symmetrical enough to hit a single point. If the star was a little bit lumpy, or if it was spinning just a little bit, the collapse would get smeared out. The matter would rush inward, get extremely dense, but then miss the center and bounce back out. To them, the singularity wasn't a physical reality. It was a ghost that only appeared when you assumed perfect symmetry. It was a mathematical mirage. This debate wasn't just about stars. It was about whether, if singularities were real, then general relativity predicted its own demise. But then came 1963, and the ghost started to look a lot more like a physical monster. Martin Schmidt, an astronomer at Caltech, was looking at a radio source called 3C273. He realized he wasn't looking at a dim star nearby, but something billions of light-years away that was as bright as 1,000 galaxies combined. It was the first identified quasar. To produce that much energy from such a small region of space, you needed something incredibly massive and incredibly compact, exactly the kind of object Einstein and the Soviets insisted couldn't exist. Suddenly, the mathematical glitch was the only thing in the universe that could explain the pressure was on. The world needed someone to stop looking at the perfection of the math and start looking at the topology of the space itself. Everything they believed up to this point was wrong. Now I want you to sit back and really try to visualize what Penrose saw, because it wasn't a set of equations or a page of messy calculus. It was a picture. To understand his breakthrough, we have to stop thinking about gravity as a force pulling on rocks and start thinking about it as a director of light. Imagine you're standing in the dark and you switch on a flashbulb. A sphere of light goes the outer surface. The light is expanding. That seems like a law of nature. If you're far away from any massive stars, that light just keeps going, spreading out across the cosmic neighborhood. This is what we call positive expansion. But Penrose began to wonder, what happens to that sphere of light when gravity becomes so intense that it actually warps the very... He came up with a concept that sounds like something out of a Jorge Luis Borges story, the trapped surface. To understand this, imagine you're in a region of space where gravity is so fierce that it's not just bending the light, it's actually dragging the outward part of the sphere back toward the center. This is the geometry lesson that changed everything. Normally, if you have a closed two-dimensional surface, think of a balloon, and you flash a light from its surface, the outward-going rays move away, and the inward-going rays move toward the middle. But Penrose proved mathematically that under extreme gravity, there is a point of no return where even the rays you aim directly out are actually converging. They're getting closer together. The expansion becomes negative. Think about that for a second. It's like being in a room where every single exit, no matter which direction you face, leads to the exact same spot in the center of the floor. You try to run for the door, but the floor is moving toward the center faster than you can sprint. In this trapped surface, there is no out. Every path in time and space, what we physicists call null geodesics, points one way, down. What made this absolutely revolutionary was that Penrose didn't rely on the perfect star model that Oppenheimer and those guys assumed the star was a perfect, smooth sphere, which is why critics like Einstein and the Soviet school could dismiss their work as a mathematical curiosity. Reality is messy, they argued. Real stars are lumpy, they rotate, they're asymmetrical. They figured that in a messy collapse, the matter would miss itself and bounce back out. But what investigators discovered next changed everything. Penrose used topology, a branch of math that deals with the fundamental shapes and connections of spaces rather than their exact measurements, to show that once a trapped surface forms, the lumpiness of the star doesn't matter. You could have a star shaped like a potato or a lopsided pear. Once the gravity crosses that threshold and creates a trapped surface, a singularity is mathematically unavoidable. He showed that the messiness wouldn't save you. In fact, the math dictated that the trapped surface was a point of no return for reality itself. By shifting the focus from local physics to global topology, Penrose moved the debate from can a perfect star collapse to can logic itself survive a trapped surface. He proved that within the framework of general relativity, the center of a black hole wasn't just a possibility. It was a geometrical necessity. You weren't fighting against a force anymore. You were fighting against the very definition of a straight line. If you were inside that surface, the future was no longer a direction in time. It was a direction in space, and that direction was the singularity. While Penrose was walking through London, a group of brilliant Soviet physicists, led by Evgeny Lifshitz and Isaac Kalatnikov, were essentially betting an entire school of thought against the existence of singularities. You have to understand the geopolitical and scientific tension of the mid-1960s. The Soviets were the masters of mathematical complexness, and they were convinced that nature had a fail-safe built into it. Their argument was intuitive. They believed that the only reason Oppenheimer's 1939 model ended in a singularity was because it was too perfect. In Oppenheimer's math, the star was a perfectly smooth, non-rotating sphere. But real stars are messy. They spin, they bulge at the equator, and their internal gas is turbulent. Lifshitz and Kalatnikov argued that in a real, untidy collapse, the particles would have enough sideways momentum to miss each other at the center. Instead of crushing into a point of infinite density, the matter would simply swirl around, get squeezed, and then bounce back out in a grand explosion. They called this the singularities are not generic view, and for a while, it was the dominant comfort blanket for physicists who wanted to avoid the embarrassment of infinite numbers. Penrose's 1965 paper in Physical Review Letters, titled Gravitational Collapse and Space-Time Singularities, didn't just disagree with the Soviets, it demolished their foundation using a completely different language, topology. He didn't waste time trying to calculate the messy trajectories of every atom in a star. Instead, he looked at the global structure of space-time. He showed that once a trapped surface forms, that two-dimensional boundary where even the outward-pointing light is dragged inward, the geometry of the universe itself closes the doors. It didn't matter if the star was shaped like a cigar, a pancake, or a potato. It didn't matter how fast it was spinning. Penrose proved that once you cross that threshold, all paths in every possible direction lead to the singularity. There is no missing the center, because in a very real sense, the singularity becomes the future for everything inside that surface. It was a mathematical checkmate. Eventually, even Lifshitz and Kalatnikov had to concede that their bounce theory was wrong. A rare moment of scientific humility that shifted the entire trajectory of 20th century cosmology. But the story didn't stop at the edges of a dying star. This discovery caught the eye of a young, ambitious doctoral student at Cambridge named Stephen Hawking. At the time, Hawking was working under Dennis Sciama, a man who was obsessed with the idea of a steady-state universe, but was honest enough to see that the discovery of quasars in 1963 was changing the game. Hawking saw Penrose's paper and he realized that if you took Penrose's math for a collapsing star and simply flipped the film to run backward, you weren't looking at a star ending. You were looking at the entire universe beginning. If a trapped surface made a singularity inevitable in the future of a star, then the expansion of our universe made a singularity inevitable in our past. Hawking reached out to Penrose, and between 1965 and 1970, the two developed what are now known as the Hawking-Penrose singularity theorems. They used that same simple geometry of light paths to prove that the Big Bang wasn't just a possibility or a clever hypothesis, it was a mathematical necessity provided that general relativity is correct. This collaboration effectively killed the steady-state theory, and it meant that our entire reality, every atom in your body, every star in the sky, once emerged from a point where the rules of physics as we know them simply ceased to exist. They proved that the universe has a point zero, a moment of creation that remains. It was the beginning of what we now call the golden age of general relativity, turning the mathematical glitch of 1916 into the most profound fact of our existence. On October 6, 2020, the phone rang in a quiet home in Oxford, and on the other end of the line was the Royal Swedish Academy of Sciences. It had taken 55 years for the world of experimental physics to finally catch up to the mind of Roger Penrose. When they awarded him the Nobel Prize in physics, they didn't just give it for a clever mathematical trick. They gave it, in their words, for the discovery that black hole formation is a robust prediction of the general theory of relativity. Think about that word, robust. It means that no matter how messy the star is, no matter how much it wobbles or spins or deviates from a perfect sphere, the universe has no choice but to create a singularity once that trapped surface forms. The geometry demands it. The logic is ironclad. It was the ultimate vindication of that brief moment of silence on top. But even with a Nobel Prize on the shelf, the singularity remains the most profound crisis in modern science. You see, when Roger Penrose proved that singularities are inevitable, he did something terrifying. He proved exactly where in physics, when your equations start spitting out infinities, infinite density, infinite curvature, it's the universe's way of telling you that your map has run out of territory. It's like a glitch in the source code of reality. Einstein's general relativity, as beautiful and grand as it is, essentially predicts its own demise at the center of a black hole. It points a finger at that point of infinite density and says, I can no longer help you here. This is the frontier, where it's the place where general relativity, the physics of the very large, must somehow shake hands with quantum mechanics, the physics of the very small. We call it the search for quantum gravity. If you go back to the 1965 paper, Penrose wasn't just describing a dead star, he was describing a place where space and time switch roles, where the future is no longer a direction in time, but a direction in space. There is no tomorrow inside a black hole. There is only the center. And if the math says time ends there, what does it mean? Keep in mind that shortly after the 1965 discovery, a young, brilliant doctoral student named Stephen Hawking realized that if you just take Penrose's math and flip the arrow of time, the collapse of a star looks exactly like the expansion of the universe. If a star must end in a singularity, then a universe like ours must have started from one. The Hawking-Penrose singularity theorems laid the groundwork for the modern Big Bang theory. They proved that we didn't just happen by accident in a steady-state cosmos, we emerged from a geometric necessity. Today, we have the photos to prove Roger was right. In 2019, the Event Horizon Telescope gave us that glowing orange-ringed shadow of M87 star. In 2015, the LIGO detectors felt the literal fabric of space-time ringing like a bell from the collision of two black holes over 1 billion light-years away. These aren't just data points. They are the echoes of Penrose's trapped surfaces. We are living in the golden age of relativity that Roger's 1965 paper kicked into gear. Yet, at the very center of every one of those black holes lies that mystery, that point where the geometry says we are staring into the throat of a beast that we can describe perfectly with math, but whose internal reality remains a total enigma. It makes you wonder, is the singularity a physical point? Maybe space and time aren't the fundamental building blocks of the universe at all. Maybe they are just emergent properties, like the temperature of a gas or the wetness of water, and at the singularity, the water simply turns into something else entirely. The universe is not only stranger than we suppose, it is stranger than we can suppose. If this journey through the mind of a genius left you thinking, subscribe and hit the bell. Tell us in the comments.